Hey guys, in this lecture we'll start something new. We will talk about inner product spaces, and in this first lecture we will start with something very simple with the dot product, and we will talk about vector length and unit vectors, how to find the distance between two vectors, or to find the dot of two vectors, the angle of two vectors, or determine the orthogonality. And also we will talk about some inequalities such as Cauchy-Schwarz inequality or triangle inequality. And at the end, and also Pythagorean theorem. And at the end, we will use a matrix product to represent a dot product. Okay, so let's get started. We will start first with the vector length and unit vectors. Okay, so vector length and unit vectors. Like I said, this will be one of the first lectures in a series of, I assume, 3 or 4 lectures where we will talk about inner product spaces. You will see that the main purpose of this chapter, this will be the 7th chapter from the, well, usually in some books it's done before eigenvalues and eigenvectors, but I prefer to do it afterwards. Like I said, the main goal here is to talk about the Gram-Schmidt orthogonality procedure, but anyway, we'll get there. First, let's talk about vector length and unit vectors. And we have seen previously in the vector spaces chapter where we talked about vectors in the first place, right? We have seen how to add, how to subtract, and we have seen how to multiply by scalars. We have seen all these operations, but now let's remind that the vectors can be characterized by two quantities. And these two quantities will be the length and direction. This is very important, right? So we have seen this. Also, in this lecture, we will define some other geometric properties, such as distance and angle. In this lecture, we shall define other properties of vectors such as well, when I say other properties, I mean geometric properties such as distance and angle. Okay. All right. Now let's draw a picture first. Let's draw the following picture. So we want to see how we can define the distance. So this is the system, the origin here, and I have this vector v. This will be of coordinates v1 and v2. And now guess what? What I'm going to do will be the following. I'm just going to project this on the x-axis. And this will be, so we'll project here. So the distance from here to here, when I project this on the x-axis, v2 will be 0. So this guy will be nothing else than, so this guy, the distance from here to here, is nothing else than just the absolute value of v1, right? And this guy here will be nothing else than just the absolute value of V2. Now, by the Pythagoras theorem, this is a right angle triangle. We have that, this guy, let's also call this guy here, let's denote it like this. This will be what we will call the length or norm of V. Sometimes it's called the norm. Anyway, it doesn't matter which way you call it. Okay, by the Pythagoras theorem, guess what we'll have? We know that the sum of the squares of each leg is the sum of the hypotenuse. In other words, we will have that the absolute value, the norm or the length of V squared will be nothing else than just the absolute value of V1 squared plus the absolute value of V2 squared. That's the Pythagoras theorem. Or equivalently, you can write this as the absolute value of V is nothing else than just the square root of V1 squared plus V2 squared. And this is how we define the length or norm for vectors in R2. Okay. For a vector in R2, right? So that we define it by this formula. The length of V is nothing else than just the square root of V1 squared plus V2 squared, right? As you can see. Okay, great. Well, we can use this R2 as a model, right? Here, everything is in R2. And we want to use this as a model to define the length of a vector in Rn. So definition, the length or norm of a vector V, and let's say this vector will have coordinates V1, V2, Vn, right? In Rn is, guess what? Is this guy here. Plus Vn squared. So that's the formula that you see here. Sometimes, well, it's the length, the norm, it's even called the magnitude. Let's mention this, the length of a vector is also called its magnitude. Magnitude, right? Right, so we have these three words, length, norm, or magnitude. And now let me point out a remark which says the following: if this vector, if has norm 1, in other words, if the length of the vector is 1, then the vector V is called a unit vector. Okay, now let's see some examples. But before we see some examples, I want to point out some another thing, which says that, well, clearly by the definition, as you can see it here, right, in green, it's obviously this implies that the length of a vector will always be a non-negative number, right? In other words, the length of the vector v is non-negative. Right? Let's write this. The norm or the length of v will always be non-negative with equality if and only if v is the zero vector. So this guy is 0 here, and I'm going to denote it like this. The zero vector in Rn. Well, the zero vector in Rn is the guy that has all its components equal to 0. There are n of them, since it's a vector in Rn, and all of them are equal to 0. Okay, great. Now let's point out some examples. And the first example that I have in mind is, well, I want to find out the length of a vector in Rn. And now let's give some examples. The first one, let's consider in R5. Let me consider the vector v, let's say whatever, 0, -2, 1, 4, -2. Okay. So this is in R5. As you can see, it has 5 components. The length of v is given by this guy, which is a square root according to the definition that you see here above, right, in Rn. It is nothing else than square root of 0 squared plus -2 squared plus 1 squared plus 4 squared plus -2 squared. Okay, and this computation here will give us it will be square root of 25, which is fine. In other words, this is a vector of length 5. Now let's see another example in R3. Consider the vector, let's say v. Of course, since it's in R3, we'll take a vector with 3 components, and let's take something with square root, 2 over square root of 17, let's say, -2 over square root of 17. Okay, and the third component, let's be 3 over square root of 17. Right? The length of this, of v, is, well, according to the formula that I just gave you, is nothing else than the square root of 2 over square root of 17 squared plus -2 over square root of 17 squared plus 3 over square root of 17 squared. And this, as you can see, you have a square 17. There is nothing else than just the square root of 17 over 17, which is 1. So this is what we call v is a unit vector. We have seen previously, right, that a vector whose norm equals 1 is called a unit vector. Well, now let me talk about something. Let me point out another remark. And what I have in mind is the following. Each vector, since we're talking about unit vectors, each vector in the standard basis, and I think you remember this by now, what the standard basis is, for Rn has length 1. right? And is a standard unit vector, is a standard unit vector in Rn. Now it is common to denote the standard unit vectors for R2 and R3 in the following way. So it is common to denote the standard unit vectors in R2 and R3, and we'll have a special notation for these vectors as well. We'll denote them in the following: ij. This will be the unit vectors in R2, which will have components 1, 0, 0, 1. So this goes in R2. Then in R3, we'll have these unit vectors I, j, k, which will denote them in the following way: 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this goes for in R3. Okay, great. Now let's call another definition. Let me remind you, two non-zero vectors, let's say u, v in Rn, are called parallel. Okay, when one is the scalar multiple of the other. One is a scalar multiple of the other. In other words, say that is, say u is a constant k times v, right? That's what we say when we say that two vectors are parallel for some constant, from some real constant. Now, if this constant k is positive, then the two vectors u and v have the same direction. The same direction. Okay. And if the constant k is less than 0, then u and v, as you can imagine, have opposite directions. Have opposite okay, let me have opposite direction. Directions. Okay. All right. Well, now we are veering towards a theorem which will give us the length of a scalar multiple of a vector, and as you can expect, it's not a big deal to compute this. Well, let's see it. So we have the following theorem. I don't know how to call it, let's say theorem 1. And like I said, this is will give us the length of a scalar multiple. And basically it says the following. Let me consider V be a vector in Rn, and K is a scalar. And then we have the following. The length of CV is nothing else than just the absolute, okay, K, not C. KV is nothing else than the absolute value of K times the norm of V, where, just like I said, the absolute value is the absolute value of the constant K. Okay, so that's a theorem. It's very easy to prove. It's basically immediate. You just have to apply the definition, and then you will see that each component, so each vector KV will have KV1 will have components as KV1, KV2, KVN. You'll raise them, you'll square them, you'll take the square root, and guess what? You'll derive exactly the formula. Okay, the next theorem, but this is very good to know. The next theorem says the following. Theorem 2 says that if V is a non-zero vector in Rn, then, well, this is then this vector, and let me write it in this way. Let's call this U, which will be V, and I'm going to divide this by the by its magnitude or its norm. This will be a unit vector, has length 1, and has, this is important, and has the same direction as V. As V. Okay. This is what we will call, well, we said this has length 1 and same direction as V. This vector U is called the unit vector, called the unit vector in the direction of V. Okay, again, this is very easy to see. And now let's give an example where we want to find, so example, God knows this was example number 2, I think. In this example, we want to find a unit vector. Find the unit vector in the direction of, let's say, vector V, and let's pick one in R2, 3, -1, 2, and verify that this vector has length 1. That it has length 1. Okay. Let's look at it. Well, it's pretty straightforward. It tells us exactly what to do at this point, right? And let's see, well, we have to compute the unit vector. As you can see, I have this formula here, right? And this is what I'm interested in. Okay, let's do it. The unit vector in the direction of v is given by v over the absolute, the magnitude. We divide v by its magnitude, and this will be, let's see, so that my vector v was 3, -1, and 2, and I'll divide this by its magnitude, which will be the square root of 3 squared plus -1 squared plus 2 squared. Well, this will be nothing else. Let's compute this. This would be 9, 10, okay, 14. So it will be 1 over square root of 14. This will be the scalar times 3, -1, and 2. This will be, if we want to write this as a vector, as you can see, I have a scalar in front of it. So this will be 3 over square root of 14, -1 over square root of 14. And the last one is nothing else than 2 over square root of 14. So that's the unit vector. Well, that's the unit vector in the direction of v. Well, is this unit? Well, it's quite clear it is. Let's call this u. The vector u is a unit vector since we have the following. Let's look at it. We see, I look at it here, and if I want to compute the magnitude of u, which will be the square root of 3 over square root of 14 squared plus -1 over square root of 14 squared plus 2 over square root of 14 squared, which will be, well, it's obvious at this point, it's 14 over 14, which is 1. Indeed, this is a unit vector, right? Okay, this is a unit vector. As you can see, these are very simple examples of how to compute the magnitude or the norm or the length or whatever you want to call it of a vector. It's very basic. And now we want to talk about something a little bit different. Well, it's kind of the same as the length of the vector, but we'll talk about the distance. What if I have two vectors in Rn and I want to find the distance between them? As you are about to see, the distance is nothing else than just computing basically the magnitude of the difference of the two vectors. Okay, let's see. So the distance of two vectors in Rn. Okay, that's what we want to talk about now. Okay, let's see. Again, to define the distance of two vectors in Rn, we will use R2 as a model. And let's see in R2, what's the deal here. You will see that the distance formula in R2, the distance formula well, from analytic geometry, let me remind you. I think this was done in calculus 1 at the very beginning. From analytic geometry is between 2 points. Between 2 points. And let's say these 2 points are given by, I'm going to call u, the 2 points in R2 of coordinates u1, u2, and a v of coordinates v1 and v2 is given by, let me remind you that this distance, let's call it like this, d will be nothing else than uv, is the square root of u1 minus v1 squared plus u2 minus v2 squared. That's the distance formula, right? Let's draw, well, let's, in vector terminology, and then we'll draw a picture. In vector terminology, this distance can be viewed as the length of the difference of the two vectors of u minus v, right? Where u will be of is this vector of coordinates v1 and v2 and u2, and v is of v1 and v2. In other words, that is, and let's write it in this way, the length of u minus v is nothing else than just the square root, is the formula above, u1 minus v1 squared plus u2 minus v2 squared. This is how we compute the distance of two vectors in R2, right? It's the same as the formula above. And let's draw a picture so that things will be as clear as possible. Let's say we have a vector u here. Let's call it like this. This is u. And this will be components here, u1, u2. And let's say we have a vector v here. So this is v. And let's say this is v, the coordinates here are v1 and v2. And now we want to find out the distance between these two. Right? This will be nothing else than the distance u between u and v. Distance between u and v, right? Okay. And this distance, in fact, let me write it here, between u and v, we'll denote it like this, is the length of u minus v, and again, by the formula above, is u1 minus v1 squared plus u2 minus v2 squared. Okay, that's it. Now we can, I will state it one more time. The distance between two vectors in Rn this time, so we can generalize this, is given by two vectors okay, let's call these two vectors u and v in Rn is given by duv is the length of u minus v. That's it. We can generalize this formula to vectors in Rn, is the same story. And now let's see some properties of this distance. This distance has the following properties. the first one that I would like to mention, clearly the distance between u and v will always be non-negative, right? With equality, in fact, let me mention this is a property too. The distance between u and v is 0 if and only if u equals v. The second one is nothing else than just the equality case from the first one. And the third one is that duv, so it's symmetric, is the same as dvu. This is very easy to check. Anyway, let me give a quick example of, let me denote two vectors. Let's say the distance, let's consider these two vectors u, let's go in 0, 2, 2 in R3, and v to be the vector 2, 0, 1. So these two vectors are in R3, and the distance between u and v is given by this guy here, duv, which is nothing else than just the length of u minus v. And we can write this as the length of this vector 0 minus 2, 2 minus 0, and 2 minus 1, which is nothing else than the square root. Now we are applying the definition of the length of a vector. So this will be negative 2 squared plus 2 squared plus 1 squared, which will give us 3, right? Which is 9, square root of 9, which is 3. And you can come up with plenty other examples. Well, it's quite clear how would you compute the distance between two vectors. Now I want to veer towards something else. So we have seen how we find the length of a vector. We have seen how to find the distance between two vectors, but now I want to see how to find the angle of two vectors. And for this, I will need what we will call the dot product and the angle between two vectors. Okay. And now I want to find the angle. Let me just draw a picture directly. So let's say I have these two vectors. Let's call this u. So this is my vector u, and this is my vector v. As you can see, the distance from here to, let's say, origin to u will be the length of u, and this guy from v will be the length of v. And we have seen the fact that this guy here, the distance between u and v, is nothing else than just the length of u minus v, or you can also say is the same as the length of v minus u. That's the picture. And now between these two vectors here, I have this angle theta. And we want to find out this angle theta. So again, this is in R2. Well, R2 will serve as a model. And now let's see. Theta is the angle between the non-zero vectors u and v. Right? We have these non-zero vectors. If one of them is zero, there is nothing to talk about. It's not interesting to talk about that. And let's just say these vectors u has the coordinates u1, u2, and v is v1, v2. And I want to find out the angle between these two. How should I do it? Well, from Euclidean geometry, and let me mention that this guy, theta, theta is between 0 and pi, right? And now let's see, how can we do this? There is a so-called cosine law from elementary geometry, which says the following, which says that the cosine of theta is nothing else than just the length of u squared plus the length of v squared minus the length of u minus v squared, and everything over 2 times the length of u times the length of v. That's the cosine law. And equivalently, which is equivalent to the following. We can express the cosine of theta in the following way. Cosine of theta will be nothing else than just will be u1 v1 plus u2 v2 over the normal of u times the normal v. So we can express it in this way. And there is something about this guy here. This guy here is what we will call the dot product between u and v. Let's mention this. The numerator of the quotient above is nothing else than just the product, is the dot product between u and v. Right? And we'll denote this, and it is denoted by this. U dot v is u1 v1 plus u2 v2. This dot here, this is what we'll call the dot product. Right? Okay, now we can, as we have seen previously, we can generalize this scenario from R2 to Rn. And we'll have the following definition. We'll define the dot product in Rn. The dot product of two vectors of, let's say, of u, of u1, u2, un, and v v1, v2, vn is the scalar quantity okay, and we'll denote it in this way. U dot v is nothing else than just u1 v1 plus u2 v2 plus un vn. So that's the scalar quantity. That's how we define the dot product for two vectors in Rn. As you can see, this is nothing else than just the generalization of the dot product in R2. And let me give you a quick example before we go on with the properties of this. The example, let's say example 4. Let's find the dot product of the following two vectors, and let's consider two vectors in R4. Let's say u to be 1, 2, 0, and -3, and v to be 3, -2, 4, and 2. Okay, these are vectors in Rn. In R4, sorry. We're not. The dot product, it's quite clear, dot v is nothing else than just u times 3 plus 2 times -2 plus 0 times 4 plus -3 times 2, which will give us, oh my, 3 plus, it will give us -7. Hope the computations are correct. And now the following theorem, theorem 3, I think, will give us more insight about the properties of the dot product. Let's mention them, properties of the dot product. All right, beautiful. And now let's consider three vectors. If u, v, and w are vectors in Rn, keep in mind that all the vectors we'll consider in this lectures are vectors in Rn. That's why we call it the dot product. You will see that next lecture when we'll talk about the inner products spaces, you will see that the situation will change just a little bit. Vectors in Rn, and k is a scalar. Then the following properties hold true. Okay, the first one is that u dot v is the same as v dot u. U dot, let's say, v plus w is u dot v plus u dot w. The third one is that if I have a constant k and I have k times u dot v is nothing else than just k u dot v, which or you can say this as k u dot kv, right? So you can, doesn't matter which way you put the scalar. The fourth one is that v dot v, when we dot v with itself is nothing else than just the magnitude of v squared. And also it's quite clear v dot v will always be non-negative with equality if and only if, well, as you might expect, v is the zero vector, right? So these are the properties. These are very important properties of vectors in Rn, and Well, let's now we want to see some of the easy examples where we can apply these properties, and then afterwards we'll discuss about the Cauchy-Schwarz inequality and how we define the angle of two vectors in Rn. Okay, now let's see an example. Let's see, example number 5, I think. I'm not good with numbers. Yeah, it's 5. Okay, let's see an example. Let's consider the vector u. Let's take something in R2 so that the computations will be easier. Let's say 2, -2, and v to be -4 and 3. And we want to find the following quantities. Okay, the first one, let's say we want to find out the dot product between these two. And then let's see, well, we would like to find, in fact, let me consider another vector, because I want to, and let's say w, let's say this will be -4 and wait. Let's say, okay, 5, 8. Okay. Find the following quantities. U dot v, then we want to find out the magnitude of v squared. And then let's say the third one should be u dot 2w, let's say. Okay, these are pretty straightforward examples. Let's do them. U dot v, this is the dot product. So it will be 2 times -4 plus -2 times 3, which will be -8, -14, right? Okay. Wait, just okay. All right. So we have computed that the dot product between u and v is -14. And now the second one is we want to find the magnitude of v, which will be nothing else than just -4 squared plus 3 squared. And this will be 25. And this will be, well, sorry, without any square root. It will be 25. Okay. And the last one, we want to find out the dot product between u and 2w is u2 -2 dot, and now let's see, this 2w will be 2 times 5 and 2 times 8, which will be nothing else than just 2 -2 dot 10 and 16. So this will be 20 and -32. Okay. So now we would like to to define the angle between two vectors in Rn. And just like we have said previously, we will use this formula here, right? Not just to define two vectors in R2, but also to define two vectors in Rn. To define the angle of two non-zero vectors u and v in Rn, we use the formula in R2. And we'll define it in this way. The cosine of theta, it will be nothing else than u dot v over the magnitude of v times the magnitude of u times the magnitude of v. That's the formula that you see here. Okay, and now concerning the angle of two non-zero vector, we have the following inequality, which is a very important thing. This will be theorem 4. And I'm considering actually proving this, why not? It's what we call the Cauchy-Schwarz inequality. Which says the following: if u and v are vectors in Rn, then we have the following inequality. The absolute value of u dot v will be less or equal than the magnitude of u times the magnitude of v. Right? Where this guy here is nothing else, denotes the absolute value of the dot product, u dot v. Okay, and now let's see the proof of this. The proof is quite nice. Now, if one of the vectors, let's say u, is 0, then it follows that u dot v in absolute value is nothing else than just 0 dot v, and this is the magnitude of u times the magnitude of v will be nothing else than just 0 times the magnitude of v, and this will be 0. So we have equality. 0 less or equal than 0, which is true. In fact, we do have equality. Okay, this is what happens if one of them is 0. Now, let's assume that u is not 0. And let lambda be any real number and consider the following vector. We'll consider let's say lambda u plus v. So the scalar multiple of u, and we add it with the vector v. And now what we're going to do, we're going to look at the dot product between this vector lambda u plus v and itself, right? In other words, we have that the product lambda u plus v dot lambda u plus v, we know that this is non-negative, right? Based on the properties that we above. You see, the dot product v, just look at property number 4. The dot product between v and v is nothing else, it's or phi. It's non-negative with equality if v is the null vector. In other words, we dot lambda u plus v with itself. This dot product will be non-negative. But on the other hand, if we compute this, if you look at it, this is just quadratic. And I'll leave it to you as an exercise just to compute this. After some computations, this will give us u dot u lambda squared plus 2 u dot v times lambda, right? Plus v dot v. And I know that this is a quadratic function. And I know that is non-negative. Well, let me explain it a bit. Let me consider u dot u, we'll denote this by a. B will be 2 times u dot v, and c will be v dot v. And we have the quadratic inequation or inequality a lambda squared plus b lambda plus c is non-negative, right? Well, this implies that the discriminant, since this is let's call this f of lambda, as you can see, this quadratic inequality is non-negative, and the coefficient here is again positive, right? This implies that the discriminant of f of lambda is negative, right? This is just basic algebra from the quadratic equation. In other words, the delta of f lambda in this case will be, well, usually it's b squared minus 4ac, which is not negative, right? Once we translate this, or equivalently, if you want, b squared is less than 4ac. Okay, great. And this equality here, this translates into the following: 4 times u dot v squared is less or equal than 4 times u dot u times v dot v. And again, or this will be u dot v squared is less or u dot u times v dot v. Or if we want to take the square root, this will be equivalent with the absolute value of u dot v is less or equal than the square root of u dot u times the square root of v dot v, which is nothing else than just the magnitude of u times the magnitude of v. And that's it. End of the proof, right? It's a very nice proof, and it's a very important inequality. And in fact, you can verify it on any vectors if you want. You will see that the absolute value of the dot product of any two vectors will be always less or equal than the magnitude of the first vector times the magnitude of the second vector. Now, this inequality, this very important inequality, the Cauchy-Schwarz inequality, allows us to define the angle between two non-zero vectors in Rn. The Cauchy-Schwarz inequality allows us to define the angle of between two non-zero vectors in Rn. In Rn. So we can extend the definition to Rn, and well, and let's write it. So this will be the cosine of theta is nothing else than just u dot v over the magnitude of u times the magnitude of v, for theta between 0 and pi. So that's the angle between two vectors in Rn. So this is how we compute the angle of two vectors. Well, let's find a quick example. Let's do a quick one. Example number, I don't know, 6. Okay. Let's say find the angle between vectors, and we'll deal with the following two vectors, and we'll consider some vectors in R4. The first one, let's say it's 4, -4, 0, 2, and -2, and v will be 2, 0, 1, -1, and 1. Okay, these two vectors. Well, by the definition above that you see, cosine of theta, well, let's write it. Let theta be the angle between u and v, right? And by the definition above, as you can see, cosine of theta will be nothing else than just u dot v over the magnitude of u times the magnitude of v. And I think we computed this earlier, the dot, but anyway, it's easy to see. I'll let you do the computations. The dot product, I think it's -12, if fine. And this would be root 24, and this one will be root 6. And this will be nothing else than just -1. Well, you know that the cosine of an angle is -1. Well, it's quite clear that the theta will be equal to pi. That's the angle between this. Well, it kind of makes sense if you look at u and v, right? Because u is nothing else than just -2v. Let's point out this remark. They're kind of in the opposite directions. The vectors u and v are in the opposite directions. Since u equals -2v, right? So that's, well, if we go back to the formula, if you look, right, the cosine of theta is u the dot product between u and v over the magnitude of u times the magnitude of v, well, you see clear that the denominator is always non-negative. And now we got a negative result here. As you can see in our example, the cosine is -1. Definitely the problem was the numerator, it was not the denominator. So let me point this, the dot product can be negative. And now let me give you some, let me remind you some values for which you can find the angle between two vectors. And let me draw some pictures here. We have the following instances. Let's say the first one is what I have here. This is the vector u, this is the vector v, and let's go in this direction. And the angle between them, this is theta, right? The angle between them, theta here clearly is pi, and the cosine of theta is -1, right? Okay, now let's see the second situation. Let's say that we have vectors like this. Oops. And this is the angle, this is u, this is v, this is the angle theta. And let's say in this case, theta is between pi over 2 and pi. So it's obtuse, right? This is what we call, okay, this is the first one, is opposite direction. This is the obtuse angle. In this case, the dot product uv will be less than 0, right? This is what happens. Now the third situation is when we have a right angle triangle. So the vectors, what we will call them, will be called perpendicular, u and v. And here the angle theta is right angle. uv is, the dot product is 0, right? And in this case, theta is pi over 2. The fourth situation is when, okay, when we have acute angle, right? So we'll have something like this. This is u, this is v, and this is theta. So acute angle. When the dot product between u and v will always be positive. And here, the angle theta is between 0 and pi over 2. Now the last situation, the fifth one, is the following. When we have the same directions, right? So we have the vector u here, and this is v. So they're in the same direction. So theta in this case is 0, and cosine of theta is 1. This is the same direction. Right? And now we want to mention something. So these are the situations, as you can see. And now these vectors that have their dot product equal to 0, they're called in some way, and we'll call them orthogonal vectors. So definition. Two vectors in Rn are orthogonal if the dot product u dot v is 0, is a 0 vector. And there are plenty of examples of orthogonal vectors. Anyway, I'm going to skip the example. And now I'm going to do the following theorem, which concerns another inequality, very important, triangle inequality. And this inequality says the following: if u and v are vectors in Rn, then guess what happens? The following inequality holds true. The magnitude of u plus v is less or equal than the magnitude of u plus the magnitude of v, or the length. This is a very, very important inequality. I'm going to skip the proof because of we don't have too much time, but the proof relies heavily on the Cauchy-Schwarz inequality. Okay. Well, I'll just explain the basic idea. Well, you're going to look at this guy, right? The length of u plus v, you square it, then you apply the properties of the dot product, and then at some point, once you do this, you will apply the Cauchy-Schwarz inequality, and then everything will just follow immediately. Well, we also have another theorem which will concern the orthogonal vectors, and we'll call this the Pythagorean theorem for vectors in Rn. And it says the following: if u and v are vectors in Rn, then u and v are orthogonal if and only if, guess what, the following equality holds true. The length of u plus v squared is nothing else than the length of u squared plus the length of v squared. In other words, there is no dot product here between u and v, it just vanishes. Well, it's actually 0. So this is what happens between two orthogonal vectors. We'll have this relation between them, right? Okay. And now the last thing that I would like to mention, and probably I'll give an example and then I'll stop here for today, is the following: the dot product and we want to see how this is related to matrix multiplication and matrix multiplication. Well, we have seen that previously in previous lectures that it is often very useful to represent a vector in Rn as an n by 1, a column matrix, right? So we'll denote this U, so let's denote this as a column, n by 1 column matrix, U1, U2, Un, and V to be V1, v2, vn. So these are n by 1 column matrices, right? Well, guess what? If we want to represent the dot product between these two vectors, if you want, between u and v, is represented by, and let's write it in this way, u dot v is nothing else than u transpose v, which will be nothing else than just u1, u2, un, and now we're going to multiply by v1, v2, vn, and this will be nothing else than just u1, v1 plus u2, v2 plus un, vn. Okay, and that's it. All right, now let's see an example of this, how to use matrix multiplication to find a dot product. Example number, I think 7. I hope I didn't. The dot product of the vectors, let's pick some vectors in our 2 by 1 column vectors, 2, 0, and v is 3, 1. Okay, is given by u dot v is nothing else than just u transpose. So we're going to transpose the first one and we're going to multiply by the second. So this will be 2, 0, 3, 1. And now based on the above formula, this will be nothing else than just 2 times 3 plus 0 times 1, which will be nothing else than just 6. That's it. Anyway, you can find plenty of other examples. These are very, I would like to say a few applications, especially in engineering. These are very important in engineering. For example, electrical engineers use the dot product to calculate the electric flux or the magnetic flux, and the properties of the dot product as well. Anyway, I think I'm going to stop here for today. Next time we'll talk about the actual inner product spaces. You'll see that the situation will be a little bit similar, to Rn, but this time we'll consider an abstract vector space. So we'll replace Rn with an abstract vector space V, and we'll see if what kind of properties are still valid in that abstract vector space. Okay, thank you very much. I'll stop here.